Module 17 has to do with the t-distribution and the use of the t-table. So we're going to recap as far as why we use the t-distribution and what brings that about. Okay? The first thing we want to talk about is, I'll take this right out of the book, central limit theorem. Let's bring that up so everybody can see it. Okay. The importance of this, let's go over. This is what makes statistics work. Okay. I remember when I was a student back about 3 million years ago, I could never figure that out, and I never got an answer to that as far as, well, wait a minute, they talk about everything in the book. Normal this, normal that, and various distributions. How do you know something's normally distributed? Well, I've discussed this a little bit in class, but the thing is that if we don't know, we don't really care. Okay? The central limit theorem is telling you that the important thing here is process. Look at what it says. It states that as the sample size increases, the shape of the distribution of the sample means taken from the population with mean mu and standard deviation sigma will approach a normal distribution. The distribution will have a mean mu, standard deviation sigma divided by the square root of n. What the heck does that mean in English? Okay, the important thing in here is this thing here. The shape of the distribution of the sample means. Okay, in other words, we're not talking about individual readings. The process is extremely important. Okay, let's look at it this way. If you have a population that is not normally distributed, I don't care what the distribution of the population is, as long as we're dealing with numeric data. Okay, if instead of looking at the individuals and talking about individuals, I take a random sample, a simple random sample. Okay, then if I measure 25 items and take and calculate the mean of those 25 items, okay, if I save that and say, okay, that is the mean from the first sample. If I go take another sample of 25 items and take that mean, that's the second mean. Okay, those sample means will be normally distributed. Okay, even if the population is not normally distributed, the means of the samples, as long as you're dealing with simple random samples, will be normally distributed. And as the size of the sample increases, that will get closer and closer to the normal distribution. Okay? As the sample size is smaller, it'll be off a little bit. Okay? And this is the theory behind it. This is why statistics can work. Okay, now, the question comes up is, how far off will it be? As I mentioned in a previous thing, this was come up with, it was called the student distribution, the student t-distribution, and it was discovered by the hard work over years of a man called Bill Gossett, William Gossett. He was a quality control person at Guinness Brewery and responsible for quality control. Okay? He did sampling. Great job. I think the old song, 100 Bottles of Beer on the Wall, probably was attributed to him. If you go way back, remember when you'd sing that as a kid riding on bus trips? Okay. Now, what he did is took samples of various sizes and compared that with the normal table, okay, and came up with a table they called the student t-distribution. Remember here in the normal table, we used Z. He said, wait a minute, this isn't going to be normal, it's going to be off a little bit. He used T. And that's where we get the name t-distribution. Okay, he couldn't admit this to anybody as to what he did because this was trade secrets. They didn't want their competitors knowing it, but Gossett felt this was so important to the mathematical community that he published his findings under the name of a student. And this is where it took years before anybody knew who did the stuff. Okay? And this was called the student t-distribution. Now people drop the student name. You still see it in some of the, if you read a history of math book, you'll run across this. But it's called the t-distribution. Okay. What I want to do is show you where we get. Remember when we did the 95% confidence interval, we looked up what has 97.5% to the left of it. Let's bring this up. Let's do this. Okay, there we go. 97.5 is right about there. And it was 1.9, and up above was 6. Okay? And so we said 97.5, and the other, the minus 196, gave us 2.5. When you subtract them, you had 95% in the middle. Okay, remember that. That's important. Now, let's shift over to a t-table. What does that look like? Well, I copied this right out of your book. This is in the back tables in your book. All right, now, let's look at this. Up at the top, it talks about an 80% confidence interval, 90%. Remember, the confidence interval is two-sided. Okay, so if this is two tails, there's 20%, 10%. If it's one tail, there's 10% in each tail. Okay, like on a 95% confidence interval, it has a total of 5%, and that is spread between two tails. Each tail has 2.5%. Okay, so if I'm doing a two-tailed test, 95%, I'm in this column. If I'm doing a one-tailed test for 95%, I'm over here. Okay, so the number that I use for a one-sided, see here they're calling it tails, a one-sided test at 95% is going to have the exact same test number as a two-sided test, okay, at 90. So 90% one side is the same as 95% two-sided. Okay, that's what I said. The one-sided is easier to show. All right, now let's go look at the thing. What's this DF down the left-hand side? This is my degrees of freedom. And for a t-test, it is defined as n minus 1. N is the size of the sample. Okay, so if I took 25 people, let's leave that right there. Okay, if I had a sample size of 25, okay, the degrees of freedom would be 24, one less than 25. Okay, so if I wanted to do a 95% two-sided test, what would my test number be? 95% is here, come down to DF of 24, okay, and what do I have? Okay, I'm at right here, 2.064. Now, what was the number on the normal distribution? 1.96. Okay, so I've got to be a little bit bigger. How much bigger do I have to be sure of myself? Now, if I'm only sampling 25 people, then I've got to be out 2.064 standard deviations to be sure that, I got to be beyond that for a 95% test. If I was doing a one-sided 95% test, okay, then I would be in this column, and I would come down. Again, if I did 25 people, I'd be DF 24. I'd come down here, and it would be 1711. Now, if you remember the number from when we did confidence intervals, what was the 90% confidence interval? 1.645. Okay? And if you want to check these things, let's go down to the bottom of the table. Let's see. Okay, right there. See where Z, infinity. In other words, this is the normal number. Okay? For 95%, it's 1.96. For 90%, it's 1.645. Okay? And if you go back to the top of the table, let's see. Okay, this is telling you. So this is the 95% one-tailed, 90% two-tailed, 90% confidence. 95% confidence, 0.025 one tail, 5% two tail. Okay? Does everybody see how to do it? Now, in your tail, let's slide this over. They've got some other numbers. 95, there's 98, 99. That's all they give us. Okay. Now, if you're comparing this to the normal table, if you go down to the bottom, okay, these numbers down in the bottom row match up exactly with what is in the normal table. Okay? In other words, if you had a huge sample size, but let's put this in context. Look at, if I've got a sample size of 1,000, I got 1962 instead of 1960. Okay? If I've got a sample size of 101, okay, because I've got to be one more than this, 1.984. Look, 2 is up here on DF 60. Okay? And so this is why if they're doing ballpark numbers, 95% is approximately 2 standard deviations. Well, if I've got a sample size of 61 or more, yeah, 2 covers it. Okay? But when we come down here, what did we say we needed for the stuff? Is 40, and I'm at 2024. Okay? And 40 is big enough that that covers all kinds of sins. But you'll notice, now look at what happens at the bottom part of the table. Let's go down. Okay, DF1. In other words, I've got 2 items. How many standard deviations do I have to be out for 95%? 12.706. Okay? This is why it's telling you, as far as look at these numbers on small sample sizes. 4, 3, 2, okay? Do you notice how it starts coming down, right? Here, 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 but 10, 15, 20. Okay, if we're going out, and you want to get out to 1.9 is about 2.1, okay? You see here, you got to get to about a 20 sample size to where, you know, you don't bump up to 2.1. I mean, if you've got to be below 2.05 to round off to about 2, let me bring this up and let's look at it. Okay, where are we at? 2.048. Okay, and that's what? DF of 28. Remember I said a little over 25 and stuff like that. And this is telling you how far off you're going to be. It isn't that great a thing, so it's approximately 2, right, if you're rounding off to 1.96, and you know, if you're accurate to 1 decimal place, you've got to be up here in the high 20s or so. Now, some books will tell you 30 will cover the things. Some people will say 40. If we slide this up, when we get to 40, 2.021, okay, that is close enough to 2 and stuff like that to really get you there. But you notice how when you get over 2.0 is where? I'm in the wrong column. Okay, 2.0 is at 60. You get 61. You get up there, you know, between 50 and 100. You're pretty darn close. You know, 2 standard deviations covers 95%. Okay? And this is why when we're dealing with stuff, if you're just doing a rule of thumb, you take a sample out there. If you got a decent sample size, 2 standard deviations that cover 95% of what's going on. So if you take your number minus the mean divided by your standard deviation, and where does your standard deviation come from? Remember, you don't need to have the population standard deviation. This is what, when we're doing t-tests, you take the data, you put it into your calculator, or you put it into Excel. When you're working your homework problems, what do? You take and put your data down in a column form, going straight down, and then highlight the whole thing. You put it over into, you'll see this when you do your homework and you follow the instructions in the book as far as using the computer. But you just go into sample statistics as far as you go into the data, and you have it with the analysis tool pack activated, you could get all of this stuff just by clicking on descriptive statistics. It'll give you a mean, standard deviation, everything you need. As a matter of fact, the t-test is canned in there, your two-sample t-test, your match pairs t-test and stuff. I'll show you how to do these later on using your calculator, so if you don't have a computer around, but you're not going to do this stuff by hand unless your mother raised a fool. Unless you're very anal retentive and like playing around with numbers and love wasting time playing with this. Anyway, now I bet you never thought you'd hear a math teacher telling you something like that. Anyway, this is how we use the t-table. Going through, we have to figure out what is the level that we're testing at and what is your degrees of freedom. Let's go back to the top of the table. What happened to this? Okay, there it is. Okay. Going to the top of the table. Okay. The DF, once we figure out sample size, 1 minus the sample size gives us a row. So if I have a sample size of 10, I would be in row number 9. Okay? These are the numbers I'd be working with. Then I look at that. What is my test? If I'm doing a 95% two-sided test, then I am up here at 5%, okay, 95% confidence, 5% in my tails. Alpha is the type 1 error in the tails. If I could have a 5% error, so 95% chance right, I've got to be out 2.262 standard deviations. So I do my test, my number minus my mean divided by my standard deviation. If that's more than 2.262, then I've got significant change. If I'm doing a one-sided 5% test, I'm in this column. I only have to be out 1.833. Okay? Same calculation. My number minus the mean divided by the standard deviation. And remember, the standard deviation has to be adjusted for the sample size. What am I talking about? Let's put it down in terms of a formula, because this is important enough. No matter what you're doing, whether it's normal or T, the process is you take your mean. Whoops. Okay. Subtract the mean of the population. Divide by, I'll put S for standard deviation, okay, over the square root of n. This is called the standard error of the sample mean. Okay? S sub E sometimes. I calculate this from the sample. Okay, so I take the sample, I get the mean, and I get the standard deviation. Then I divide my standard deviation by the square root of the sample size, and I go mean minus the population mean divided by my adjusted standard deviation. This is my calculated T number. Okay? What I showed you before is what they call T star. This is the table T number. Okay? If my calculated T number is bigger in size than the table T number, then that is significant. That shows change or difference, whether it's a one-sided or two-sided test. If the calculated number is smaller than the table number, then no change. The null hypothesis holds in place, and I have to conclude no significant change. That's how I do the t-test, and that's how I use the table to be able to do the test. Thank you.